All right, so let me recall what we have done last week very quickly. So last week we discussed a notion of cycle, which is a closed path in a graph. We had the notion of girth, which is the size of the smallest cycle. I introduced the notion of Hamiltonian cycle. It's a cycle where you go through all vertices. And also I introduced this notion of Eulerian tour. This is a path where you go through all edges, but only once. And there was a statement about Eulerian graph, what is a necessary and sufficient condition in order to have an Eulerian graph. And now there is a solution on the website. You can find it. I also introduced the notion of weighted graphs, where you have one more information. You have this omega, which give a weight or a number. It associates a number to all edges and to all vertices. So in fact, it's made of two functions, one which give a number to every vertex and one which give a number to every edge. And yeah, you can also discuss what is a weighted length in this framework. Then I introduced the notion of adjacency matrix. This is a way to encode all the information in the graph. So because you can, when you write a computer program, you cannot draw a picture. You need a way to encode this information. You can do it with this notion of adjacency matrix. Be careful if you use this, or if you read something about this, check the conventions, because sometimes the conventions are different. And I also at that time introduced the in degree and the out degree whenever you have graphs which are oriented. An alternative way to describe the information is to use an incidence matrix, which is not a square matrix, while this one is a square matrix. It's equivalent, but again, you have some conventions. I didn't speak, but in the notes, you can find also a third way to encode this information with incident table. Then I introduced the notion of isomorphism of graphs. When you have two graphs, you would like to say if they contain the same information. Maybe the picture is different. I gave some examples, but do they contain the same thing? And I define what is the isomorphism of graph. It's, again, two functions from one graph to another one. These functions have to be bijective on the set of vertices, bijective on the set of edges. And in addition, you have a compatibility condition. If you take an edge with two endpoints, then you send with F this edge and look at the two endpoints. It should be the image of the first endpoint and the image of the second initial edge endpoint. It's called the compatibility condition between the function fv and the function f. And then if you have such an isomorphism, you say that the two graphs are the same or they are isomorphic, and we use this notation. And finally, I introduced this notion of graph invariance. When you want to compare if two graphs are the same or are isomorphic, the easiest way is to show that they are not. And if you have one criterion which tells you that something is different, then these two graphs cannot be isomorphic. So this is the notion of graph invariant. They have to be preserved by isomorphism, and we started a list of graph invariants. So as I said, it's useful for showing that two graphs are not isomorphic. It doesn't tell you that they are isomorphic, but it can tell you that they are not. Finally, about reports, if you want to get credits, and most of you want to have credits, you have to write a certain number of reports. The number is not fixed. It depends on many parameters, but I encourage you to start very quickly. You can either work on some exercises available in books, on examples, on some statement that I do not prove, or on some remarks. You are free, but please do something. And you can work by pairs. You can also, you don't have to type. You can give me 100 reports. That's also fun. If you have any question, you can interrupt me at any time. And the same for those online. If you want to ask a question or make a remark, you can just unmute yourself.
Is there any way that, for example, if the graph invariants are the same, can we like impose an extra condition?
Okay, the good question. Let me say it because not everybody could hear it. Suppose you have a list of graph invariants and two graphs share exactly the same invariance. Is it enough? It depends on the size of the graph. If you have a big graph and you have only a list of 2 graph invariants, probably it's not enough. Still, if the graph invariant is take all degrees, no, it's still not enough. No, but yeah, for very small graph, a short list of graph invariants can be enough, but usually not. It's difficult to have a necessary and sufficient list of invariants. It depends on the situation.
So we can't really like impose an extra condition.
No, no. It's as I have written. It's more for showing that something is not. If you want to show that something is, it's probably not sufficient. Or you have really to find all invariants, and in this case, it means you can fully describe these 2 functions. You have better write these 2 functions. 2.3. What is an automorphism? Automorphism. Yes, half of a chart. Sorry? Yes, of course, if somebody wants to write a code, next week I will start with a few very simple algorithms. So if somebody wants to implement some algorithm or find an exercise where you have to implement some computations with an algorithm, yes, you can do it, sure. No, it's completely free. So automorphism on symmetries. And it's related with this notion of graph invariant. I have to explain what is this, but you can let me start with an example. It's probably easier. Let me take a very simple graph with E1, E2, E3, and I also need to give a name to the vertices, X2, X3. And let me do a second copy of it, but I change the names. E2, E1, E3, and now X3, X2, and X1. So we have 2 times the same graph. I can construct a function f, which is made of 2 functions, fe and fv, which these 2 functions satisfy the relation here. So in fact, I'm constructing an isomorphism of graph, but in this case, it's very simple. So what are these 2 functions? At fb of x1, I send x1 on x1. fb of x2 is probably x3. And fb of x3 is x2. This is not enough. I need to say something also about fe. So fe of e1 is going to be e2. fe of e2 is going to be e1, and fe of e3 is e3. So what we have realized here is isomorphism. But here it's so clear that we call this symmetries. Let me now give you the definition. And by the way, this relation you can check is satisfied. And what does it say? It says x2 here is between x1 and x3. Its image has to be between e1 and e3. The same take x3. x3 is between e3 and E2, and the same here. So you can check that the relation which was written here, this compatibility condition, is satisfied. So what is automorphism? Or definition? An isomorphism, what I have described here, an isomorphism from G to G is called an automorphism. It's an internal isomorphism. This is the definition of automorphism. It represents a symmetry of the graph G. So I'm able to construct a function, an isomorphism from the graph to itself just by exchanging the vertices and the edges in a coherent way. And by the way, this is not the only one. For this small picture, the second example, I can also do a kind of rotation. So here I did a mirror symmetry. You can see I just exchange through this vertical mirror, but I can also define a new one, and I let you do the picture. So you can send f p of x1. Oh, I didn't even write it, so let me do it with a picture instead. The same x1, x2, x3, and we have e1, e2. You can send it with a new f, or now I do a kind of rotation, x1, x2, x3. This is clear. I just have to be careful for edges. Now I have e1 here, e3, and e2. And you can check that I have respected the compatibility condition. E2 is between x1 and x3. E2 is between x1 and x3. So we have, in this case, two different automorphisms. So far, so good. But what can we say about these automorphisms? Whenever we have such a symmetry, what can we say? Some of you already know the concept. Remark. The set of all automorphisms of G is, what is the end of the sentence? For some of you, it should be easy. Yes, it's a group. It's a group. Because I gave a course on group theory. So what is a group? What does it mean? It means in a group, you always have an identity, which is doing nothing. And indeed, I can define f being f of x1 is x1, f of x2 is x2, f of x3 is x3, and the same for edges. You do nothing. This is a automorphism. It means there is an identity. There is f, which is identity. Usually we call it identity like this, which means f of xj, f v of xj is xj, f v of xj, of ej is, or ek.
No, fv.
F, thank you. You do nothing. So you always have such an automorphism. Then check, so this is the first thing, to if f is, I give a name, is a group denoted out of G. Out is for automorphism, so we denote this group by automorphism out of G. So if F is an element of this group, so if it realizes automorphism, then you can check its inverse. Then F minus 1 is also in this element out of G. Why you can define F minus 1? Remember, it's made of two functions which are bijective. So you know bijective, you can go on the opposite direction. What you need to check? You need to check the compatibility condition for the inverse. It's not for free. You have to check that it's satisfied. But at least you can define F minus 1, but you have to check that the compatibility condition is satisfied, but it's not difficult. And the third condition, so you have existence of identity, existence of inverse, and if F and G belong to out of G. Then the composition. F and then G is also an element of this out of G. And what does it mean if you, on this, if you first do this mirror symmetry, and then with the result you do a rotation, you get the same picture. And the composition is an automorphism. You can check this, it's not difficult. And if you have these three conditions, it's what we call a group. So it's quite good to have such a structure. When you have one, or if you have two, you can even do the composition, and the composition is another element of the group.
Well, Professor.
Yeah?
Can you give a specific example of automorphism outside of your graph theory?
Sorry, I couldn't hear. Can I give?
You can see my message in the chat box.
Okay, so 1 second. Okay, he's asking about example of automorphism outside of graph theory. Yes, probably we can find plenty of examples, but I prefer to continue about graph theory. So please send me an email and I will answer this question. Now we are discussing graph theory. I cannot give an answer for something outside of graph theory. But yeah, if you send me a message, I will reply. Okay, so we have this nice structure of a group. And this was the first remark, probably. And there is a second one, which is also quite simple. If G is simple, remember what means simple? No loops and no double edges, so no multiple edges. And undirected, no orientation on the edges, automorphism can be described by permutations of vertices only. So it means if you have a graph which has no double edges, so this doesn't occur, and if you have no loops, so really the simplest graph like this, then you don't really have to define the two functions because this edge is completely determined by knowing X and Y. If you know X and Y, you know that there is an edge. Or, yeah, this completely describes this. So it means you can reduce the information. And when you describe these automorphism, you just need to say how you change the vertices. So in the note, you have an example of permutations. I just list X1 goes to X3, X2 goes to X5, X3 goes to blah, blah, blah. And if you have this information, you have everything. So you can, in this case, you can describe completely automorphism by just permutation of vertices. Think about it. It contains everything. And there is an example in the notes. But of course, if you have multiple edges or if you have orientations, you have to be a little bit more careful. Since I just want to take 3 minutes for one thing. We have a group. There is one notion which is completely natural in this setting, and I want to introduce it, even if it's not directly related to graph. So and usually a group, we use the letter G. But I cannot use the letter G because G is already used for graph. So let H be a group acting on a set. I take it slightly more general because it's natural. On a set X. So in what we have seen, this H, in our example, is this group of automorphism, and the graph on the set X is G, but I just want to be slightly more general for this definition. Then what is, for any point in this set X, what orb of X, which is called the orbit of X. It's a definition. You have a set, you have something acting on it. So you take a point and you look at all the image of this point. So this orbit of X, let me describe it, is the set of H of X for any H belonging to the group. So in the example before, in the triangle, I started with, let's say, X1. One action was this rotation. So the orbit of X1 was with the identity. You have X1, you don't do anything. Then you start the rotation, you arrive here. So this point is also in the orbit of X1. And then if you do a second rotation, you arrive here. So it means there is only one orbit in this case. If you make a more complicated graph, and I will give an example, you may have different orbits. So you act with the group on one point and you collect all these points. You act with any element of the group on X and you take the set of all these elements. So this is a quite natural notion of orbit in graph, in group theory, in dynamical systems. So for those who came to the course on dynamical system, differential equation on dynamical systems, we also had this notion of orbit, which is quite natural. Okay. And what is the key observation? Yes.
In particle H, they are a pair of functions, right?
In the previous example, yes.
But
Here I'm just doing it more generally. So you're right. If X is a graph, if H is a group of automorphism, each element of this is a pair of functions. So H is two functions, but also any point, I should either take just the set of vertices. If I want to do this, the image of the set of vertices, I can also look at the set of image of edges. I will come back to this example in a second. So I just wanted to write it in general. But what is a key observation? What can you say about orb of X and orb of Y? Take X or Y belonging to X. Think about it. You look at the image of X by all the elements of the group. So you do the same for Y. You have only two possibilities. Either you have an equality, and this is what happened here. I started with X1, but if I start here and I take the orbit of X2, I get the same 3 points. So you have either an equality or what? No intersection, yes. It is empty set, nothing. Because as soon as you have one element in the intersection, they are equal. Think about it. If you act with your group, if you have one point in two orbits which is the same, then you can cover the two orbits, so it means they are the same. This is a nice observation, which has nothing to do with graph theory, but it's whenever you have a group acting on a set. Let's come back to an example in graph theory. This example is also in the note. Oh, by the way, I also put the summary or the reminder at the beginning. It's also available on the website, so you don't have to copy at the beginning. It's also available. This observation says that X can be partitioned. I will explain into orbit. What does it mean? Okay, it's a little bit abstract, but you have a set X. You take a point. You look at its orbit, so the set of images of this point by the group, and then take a point which is not X, or which is not in this orbit, you have a second picture like this. Take a third point, you have a third image like this, and they have no intersection. But at the end, you cover completely X if you do it systematically. This is what is called a partition. You cover X by a set of orbits, and it covers everything. This is the notion of partition. Okay, I just wanted to write this sentence. Let's come back to the example I wanted to talk about. It is in the note, but it's a graph which is not completely trivial. Otherwise, it's trivial. Okay, and I need to give names. I'm going to use numbers 1, 2, 3, 4, 5, 6, 7, 8. We have 8 vertices, and I need letters for edges A. Oh, we have one more here. Where is B? A, B, C, D, E, F, H. Of course, you can put any names, but if I want to state a result, I need to be consistent. Okay, so we have a graph like this. It should be symmetric. Sorry, my drawing is not so good. Now you can wonder, what are the symmetries? You can easily check you have a symmetry by doing a mirror through this. You can do a mirror through this. And probably you can do a rotation, but yeah, you can do a rotation by 180 degrees. So you can check what are the symmetries, and then you can realize what I said here. I can partition this set of vertices, and I'm going to do the same with the set of edges. Through this automorphism, what we have, the set of all vertices, one can be exchanged with 8. And this is an orbit. No matter which automorphism you use, which symmetry, one is going either to be 1 or to be 8. Then you have the same for the second one is 4 and 6. 4 and 6 are going together, and that's it. You have 2 and 7, and you have 3 and 5. And you can see we have all vertices, but they are put together. This is one orbit, this is one orbit, this is one orbit, this is one orbit for the set of vertices. Now for the set of edges, we have A and B can be exchanged. We have C and D. Now you can check under symmetries, you have 4 edges together, E, F, G, and H, and one single edge, I, which cannot move to anybody else. It's alone. It's under all symmetries, you keep it like this. So you have also a partition into 4 orbits. And by the way, I was wondering if it is an accident. Maybe somebody can try to think about it. Is it an accident that we have 4 and 4 or not? I mean, why is there any reason? You can wonder, and it would be nice to have a report on this. Either you find easily a counterexample, or if you don't find a counterexample easily, then you try to show that if we have 4 orbits for the set of vertices, we also have 4 orbits for the set of edges. I don't know the answer, but I didn't spend any time on this. But yeah, you can think about it. But the easiest starting point is to look at a few examples. Graph with symmetries and check what happens on a few examples. All the definitions I gave are valid for oriented graph. You found, okay, so. No, I simply don't know. are valid. So it's an accident for oriented graph.
You actually just remove the four
Oh.
outside.
Oh yeah, if I remove I,
You remove the four outside line.
no, but already if I remove this one,
Yeah, it's already
Okay.
gone.
okay. So it's an accident. Okay, good. You don't have to write a report on this. All definitions are valid for oriented graphs. However, it's more difficult. Example. Why is it more difficult? Because you have more constraints. Look, I draw the same simple graph like this, but now with orientation. How many symmetries you have, or how many elements in the group of automorphism you have less, because the mirror is no more symmetry. If you do a mirror here, then this edge is going down, and the definition for automorphism in this case has to respect the orientation. So in this case, we have only the rotations. Yes, you don't have the mirror. So as I said, we have more constraint because of orientation. But most of the time, it means the group is going to be smaller. A small lemma, which is, so a lemma is something which usually is not difficult to prove. The degree, or both the in degree and the out degree, remember, in degree and out degree are defined when you have orientation. Here we have one out degree because there is only one edge going out and one in degree, but the degree is 2. So either the degree or both in degree and out degree are constant. They are the same on vertex orbits. What is a vertex orbit? You can guess. You can look at this example. These are vertex orbits. We have 4 vertex orbits. And of course, these one are edges orbits. And indeed, you can check if in one orbit, let's check one example. 1 and 8 should have the same degree. 4 and 6 should have the same degree. 2 and 7 the same, and 3 and 5. It has to be like this. You can think about it. If not, you cannot have a automorphism. It's one of the graph invariant I mentioned last week. Graph invariant, the degree has to be preserved under automorphism or under isomorphism. So this follows. So these degrees have to be constant under vertex orbits or inside vertex orbit, and the same for edges or edge orbit. So this is the first point in the statement. The second one is that pairs of degrees or big in, big out are constant on edge orbits. I have to speak about pairs because each edge has two degrees or 2 endpoints. Yes.
Is this again E different from the vertex set and edge set?
No. This was the initial graph with all, this is a list of all vertices. This is a list of all edges, except that instead of just writing 1, 2, 3, 4, 5 up to 8, I now put together the one which are in the same group orbit, or in the same orbit through this group of symmetries or group of automorphism.
Equivalent to the set 1 to 3
No.
versus something?
Yeah, but it's one more information. Yes, it's the same set of all vertices, the same set of all edges, but now this gives you one more information. If I just give 1 to 3 up to 8, you don't know anything about the graph. Now you know that under the symmetries of the graph, these two are going together and so on.
It's not a set of sets. It's like
Yes, it's a set of set.
This idea would be to make it precise, you should change to a union. Change each.
Okay, I see. I see your point. Okay. You want me to write. Okay. But, okay, maybe it's a little bit sloppy. So you want me to write 1, 8, union 4, 6, union 2, 7. Hevido, are you happier now? Do you feel more happy or more comfortable? Okay, yes, probably it was too short. Yes,
But if we remove the center I on that graph,
yeah,
it actually, we still have an equal amount of,
why?
because there will be two vertices and 2 edges.
Ah, you're right, we have more symmetries. Okay.
You need to bring that's why I said to remove all 4 lines, outside lines.
Okay, now write your report.
Yes.
Okay. Okay,
Which is
up to you. You're right. But apparently my conjecture for sure is not correct. Okay. We know what are automorphism, which are linked to symmetries. We know this notion of action of a group on a set. Here the set is a graph, and we have this notion of orbit. These are quite natural notions. I want to make a section about subgraphs. It contains different definitions. I already mentioned what is a subgraph, but I need to introduce a few things which are important in applications. So let G be a graph. So it's a set of vertices, a set of edges, and remember this I, if we want to speak about multiple edges, we need this. And I assume that it is not directed, be undirected. Now I take a subset of V. So maybe I start with a picture again. I'm going to take a subset of V. Okay, this is a graph. I'm going to take a subset, let's say this one. So these yellow one are S. So a subset of V is, and it's a clique. This is the definition, is a clique if whenever you take 2 elements in S, so 2 vertices in S, then there exists an edge inside E with phi of E is X, Y. Can you understand this definition? Whenever you take 2 points in S, there exists an edge between these 2 points. So let's see the yellow one, it's fine. Take 2 points, you have an edge in between. On the other hand, if I add, let's say, this point, this is no more a clique. These 4 points are not, because I cannot link these 2. There is no edge between this one and this one. So a clique is made of these 3 points. But this is only one example. I can also draw a second example. Okay, let me cheat this. Let me add Now, if I have one more edge, this is also a clique. You can check, you can connect these 4 points. So this is definition, and I will tell you why it's useful or maybe you can guess why it has some. No, let me just add, a click is maximal if not contained in any bigger click. Some also take this as a definition of a click, but it's good to have more flexibility. What is a maximal click? The blue one is maximal. On the other hand, if I take this red one is not maximal because it's part of something which is still a click, which is bigger. So we have this notion of maximal click. You take the maximal set of points which are in a click. The yellow one is also a maximal one, because the yellow one is not contained in any bigger click. So we have this notion of bigger or maximal one. Now, what is a click number of a graph? Still, the click number of G is the number of vertices in the biggest click in G. So for this graph, the click number is 4. By the way, it's not, the click number is clearly unique. For any graph, you have only one maximal number. But let me cheat again. If I draw this now, the blue one and the yellow one are two clicks with 4 elements. So the click number is 4, but I'm not saying that it's unique, that the click which realizes this number 4 is unique. But click number is unique, and it's denoted by W of G, denoted by W of G. Why is it interesting? I can look. Okay. It tells you these guys, these vertices are tightly connected. So it tells you in a graph what is the number of elements which are tightly connected. And when you deal with epidemiology, you are interested in this. Because if everybody is very connected to everybody, then you have no way to stop an epidemic. On the other hand, if you have only one group like this and all the other one are isolated, it's enough to isolate this group of tightly connected person, and then the rest, it's fine. So this click number has applications. If you want, yeah, exactly, the close contact. You want to know what is the set of close person and what is the size. The click number gives you the size of this set of tightly connected vertices. So all what I'm introducing has application somewhere. Now, what is a kind of opposite definition? Still G, which is VEI undirected. These two definitions, you can probably extend them for directed graph, but it's less natural. You can still do it if necessary. S included in V is independent. If whenever you take a X and Y in S, there is no edge. There exists no E inside the graph with I of E is equal to XY. So it's S is called independent if all points are not connected. So I can, of course, one single point is always in itself independent. But for example, this set, this vertex on this one, these two are independent. And if I add, no, in this, with these two, I have no other one. But now I could do another set. Probably this one is independent. Ah, okay, again, I cannot go through with 3. But, okay, you can see, you can construct subsets with points which have no edges between them. And then we can define this independence number, which is the maximal set of independent set. Wait, I finished the definition. The independence number of G is, and it's denoted by alpha of G is the number of vertices in the largest independence. Yes, what is your question?
This is equal to the number of.
No, it has nothing to do. This,
In this case, it would.
maybe in this case, but I'm sure now you can construct example or counterexample. No, they are not related. No.
Maybe the picture.
No, it's, we have to be careful about one example. It doesn't mean it's always the case.
Doesn't this contradict the earlier definition of the clique? The clique was
It's two different definitions. I define what is a clique. I defined what is an independent or the independence number. They have nothing to do. These two definitions. Yeah. By definition, what you mean yes, there are graph invariants. And I will mention this, yes, if you construct an isomorphism, yes, this either the independence number or the clique number are stable under isomorphism. Yes. Finally, a very short definition. I'm too slow today. What is a component? A component of G, this is easy, is a maximal connected subgraph of G. So you have a graph made of different components disconnect. So this is one component, this is different component. This is easy. You have, of course, the component number. The component number is the number of components. And probably it's denoted by C of G. The component number C of G is the number of components. This is a very easy notion, but it's good to know this word. Okay. If you have any question, always you can interrupt me. I will try to answer.
Like isomorphism, like in the case of like the epidemic, where the path the connections take don't really matter to us. Can we describe the graph just with like the orbits and clique numbers without actually having to?
Okay, no, as I said before, these invariants, these clique numbers, with the orbits is also something stable. It's there's a number of orbits, number of vertex orbit, edges orbit is also a graph invariant, but it doesn't give you the full structure of the graph. let me just rewrite one definition. So we have a graph, E, E, I, and that's it. And take a subset of edges, U inside V. What is G minus U? I already mentioned this, but let me repeat it. You take, of course, the vertices which are not in U. But what about edges? You eliminate the edges which have one endpoint in U. So it is a set of edges minus the edges with I of E. I of E is always XY, and either X or Y belong to U. Ah, no, my notation is not good. Sorry. So it says, oh, so for the set of vertices, I will do pictures. For the set of vertices, you just eliminate those in U. For the set of edges, you eliminate those which have an endpoint in U, and you take the same I restricted to something. What do I mean? Take a graph like this. If U is 1 point, I take U just this point, then I need to eliminate G minus U. You have to eliminate this one, you have to eliminate this one, and you have to eliminate this one. So G minus U is made of these 3 points plus 2 edges. Okay. And what is, now if I take a set of vertices, no, a set of edges, sorry, a set of edges, what is G minus F? This is simpler. It's the same picture, any picture, doesn't matter. If you eliminate a few edges, then the set of vertices do not change. So this is simply the same V, E minus F, and I is also restricted. So I wanted to have these two definitions for the next.
The graph below the eliminated one.
No, if I eliminate one edge, this is F. I just eliminate one edge, I don't change. No, it's not the same graph. These are two independent pictures. I'm not so bad, I can still see that it's two different graphs. I'm not good at drawing, but still. What is a cut vertex, cut bridge? Oh, okay, or I have to explain a few definitions now. No, stop question, stop. So let U inside V. Oh, no, it's a long definition, so I need several points. U inside V is a vertex cut. A vertex cut if G minus U, and this is why I recall it, has at least one more component than G. I will make pictures in 1 minute. Let me, there are 4 lines. X is a cut vertex. Cut vertex. If the point X is a vertex cut. Try to understand by yourself this definition. Cut vertex, vertex cut, and the cut vertex is also called a cut point. And number 3, I do the same with edges. F inside E is an edge cut. if G minus E has one more component, has at least one more component than G. Has at least one more component than G. And the number 4, E, is a cut edge, which is also called a bridge. E is an edge cut. Is it clear for everybody what I'm doing? Again, if you think about epidemiology, these things are important. Take a graph. Let's see. If I remove, first I deal with vertices. If I want to make, this is a one component, I want to make it in more than one component. So for example, if I remove this, now you have two components. So this is called a cut vertex. Or if I remove these two, it's also made of more than one component. So this is a vertex cut. Or you can do the same with edges. If you cut, again, it's not unique, but if I cut this one, I have more than one component, but the same now, if I cut this one, I have more than one component. And if I cut this one, I have more than one component. And again, you can imagine this has application. If you want to make your graph into two parts, you can look at the places where you have a minimal action in order to make it in two parts. So the correct notion is vertex cut and edge cut is for more than one point or more than one edge. This is a general definition. And cut vertex, which is the same as cut point, or cut edge or bridge is when you can do it with only one vertex or one edge. No more questions. Wait a second. Helvido, you have already asked many things. Okay, so these are just definitions. And now you ask me about graph invariance. So let me list again some new graph invariance we have seen, new graph invariance. So we have already mentioned for indirect graph, because we define only these two notions for indirect graph, we have the clique number, the biggest part which is tightly connected, and the independence number. We have also the C of G, which is a number of components. This is also for graph with orientations. And you can look at the number of cut point, or the number of bridge. There are also graph invariants. So we have in this section about subgraph, we have seen a few definitions related to subgraphs. And these notion of bridge and cut point are important. Is there any question? Helvido, you have a good question. Anybody else has a good question? No good question or stupid question? No. Okay. Let's move to section or chapter 3. And today I won't be able to introduce any algorithm, but I guess next week I will just mention some easy things. Section 3 is about trees. Or chapter 3 is about trees. It has many applications, and the theory is not difficult. So first, the first section is about trees and forests. Okay, first definition, what is a tree? Remember, I'm always trying to give definitions which are valid both for directed and undirected graphs. A tree is a connected graph whose underlying undirected graph, I will explain, has no cycle. Why I have to be so precise? For indirect graph, it's enough you don't have any cycle. Now, if you have a directed graph, be careful, this one has no cycle. But it's not a tree with this definition, because look at its underlying indirect graph, so forget the orientation, then you have a cycle. So it's not a tree, what you expect, still it has no cycle as directed graph. But this definition works for both. And in particular, you can observe that you have no loop. This would be a contradiction. So trees have no loop, no multiple edges. In this sense, they are simple graphs. Now, for directed graph, so when you have an orientation, this definition is fine. A priori, it's not the most useful one. So this is just a remark, and maybe somebody can think about it or work on this. For directed graph, so when you have an orientation, there is another notion which I'm not going to discuss for now. A directed graph, another notion that I want to mention. Another notion that's useful. This is acyclic. Acyclic. Remember, digraph means directed graph or graph with an orientation. What is the difference? Let me draw a picture. Clearly, this is not a tree. But it is a cyclic digraph. It has no cycle as an oriented graph. And so, as I said, this is also a useful notion. Probably later when we do some algorithm, we can think about this. So this is a parenthesis. Trees for very useful for unoriented graph. For oriented graph, the definition is fine. It's not the best one, but there is another notion which is useful for directed graph. Okay, this is just a parenthesis. So when I want to emphasize if we have an orientation or not, I will speak about an oriented tree or an unoriented tree if there is no orientation. Remarks. Any non-trivial tree, non-trivial means it's not just one point. Any non-trivial tree has at least two leaves. You remember what is a leaf? On a graph, it's one with degree, which is 1. It's an endpoint in the graph. So of course, if you have a tree, what is the simplest tree? This is the simplest tree. You have two leaves. It's just an observation. The second observation, a collection of disjoint trees is called a forest. You're not surprised. And now if you have orientations on your trees or oriented trees, there is an orientation. We say, sometimes people are calling, we say, oriented forest. And I have also found a polyforest. I don't know why, but polyforest. These are just two names that you can find in the literature, either oriented forest or polyforest. Okay, now there are a few notions, or no, first a few equivalent definition of a tree. And if somebody wants to play with these definitions, you can work on this statement. In the note, the statement is slightly more general than the one I'm going to write here. So let G, which is B, E. Since we don't have multiple edges, I can skip the I. For trees, the I is not necessary. You can think about it. Be an undirect or unoriented, undirected tree. In the note, I don't add this. So it means the statement is valid both for directed and undirected, but you need to adapt a little bit the statement. Be an indirected tree with n vertices. And then this is R equivalent. This is a mathematical statement. Are equivalent, the following description. G is a tree. Or it's equivalent to say that G is acyclic, so it has no cycle, and n-1 edges. Or it's equivalent to G is connected and has n-1 edges. For description, J is connected plus all edges are cut edge. We have seen it. What is the meaning of cut edge? It means if you remove one, you get more components. By the way, I put at least because sometimes when you cut at one point, you have take this graph and remove this point, then you get more than one additional component since you are going to get 4 components. So that's why I put at least in the previous definition. So G is connected and all edges are cut edge. 5. For any x, y inside V, there exists only one path from x to y. This sign means there exists only one. there exists only one, so I can remove this. There exists only one path between X and Y. It's not oriented, so you can say from X to Y or from Y to X or between X and Y, the same. Number 6, which is also sometimes useful. G has no cycle. And any new edge will create a cycle. And you can check, maybe it's more difficult to prove. Build a tree, add one edge anywhere, automatically you construct a cycle. So it's fully describe a tree. So no, what is this statement is all these descriptions of a tree are equivalent. But you have, if you want to work on this, you have to prove it. First you check on a picture that it seems correct, but this is not sufficient. So if somebody wants to work on this, I would be happy. Now let me just say something about unoriented tree. So this statement is written here only for unoriented tree. In the notes, you will see that it's essentially the same for arbitrary tree. So if there is an orientation, you can find also 6 descriptions like this. So now for unoriented tree. It's a theorem, which is a nice statement. Do you remember what is a central vertex? Who does remember this? What is a central vertex? Yes.
When radius is the maximum. No, yeah. The point where
It's a place. No, it's the place which is central in the graph. It's at a minimal distance of everybody. So the distance from this point to everybody is a minimal one. Yeah, the eccentricity is equal to the radius. You're right. So for any unoriented tree, there exists only 1 or 2 central vertices. Which is not true for general graph. You can construct a graph with plenty of central vertices. Think about a cycle, you have plenty. But for tree, unoriented tree, there exists only 1 or 2. It's going to depend on how many vertices you have. I'll let you think about this. What is the meaning? And it has a property. It will come back in a few minutes. In the notes, you can also find a picture which I like. I cannot reproduce it. You can draw all trees with a certain number of edges. But of course, so it means you can list all possibilities with 1 edge, 2 edges, 3 edges, and so on. But of course, you need to reduce this number. So let's look at the following definition. Irreducible tree. Irreducible tree, and you will see it's a natural definition, is an unoriented tree with no vertex of degree 2. You can wonder why I don't want to have a degree 2. Because this is a boring situation. Look, construct a tree, very simple tree. You don't want to add you know, if I want to list all possible trees, I want to avoid everything which is boring, and a vertex of degree 2 is always like this. It has one edge coming to it and one edge going outside of it. I just want to eliminate this. It's a boring situation. So an irreducible tree is a tree with no boring place, so with no vertex with degree 2. And then you can see in the notes, I cannot reproduce this. We can draw all different irreducible trees depending on depending on the number of vertices. In fact, it's the same as the number of edges, because if you have n vertices, you have n-1 edges. So if you do the list with n vertices, it's the same as doing the list with n-1 edges. And you can make these pictures, and it's quite nice. But you have to eliminate this boring situation. Okay, we know what is a tree. We know what is a forest. We have different descriptions of what is a tree. You would be happy if the tree has a root, because without root, it's not going to survive for a long time. So what is a rooted tree? This is one more information. So this is the next section, rooted trees. And there is one possible confusion. No, this is not general enough. Definition. Why do you want to have the root at the maximal distance? I can decide that the root is here. Of course, if you want to think about a root, I maybe need to modify the picture, but I'm free to choose this as a root. So the root is just one special, you choose somebody and you call it the root. So a rooted tree, oriented or not, a rooted tree is a tree with one vertex called the root. You choose one and you call it the root. And if you have colors, you put a color and you say, oh, this is the root, and I call it R. It's a rather stupid definition, but this is the most general one. But be careful about one thing. This is a little bit misleading. Two graphs can be isomorphic as graphs, but not as rooted graphs. Please try to understand this sentence, or try to find an example. What I mean by they can be isomorphic as graphs, but not as rooted graphs. And I give you an example, very simple. Okay. So far, so good. But now I decide that this is a root, and I decide that this is a root. As graph, they're the same, but not as rooted graph, because as rooted graph, I didn't say what is a rooted isomorphism, but you can expect as rooted graph, this root has to go to this one. The root of one tree is sent on the root of the other one, and you have no way to create an isomorphism which is an isomorphism, but which also sends this root here, simply because they don't have the same degree. It's impossible. So these two graphs are isomorphic as graphs, but not as rooted graphs. Be careful about this. So the root is you fix one special guy. But once you have fixed this, of course, in pictures, usually I'm going to put the root at a special place, either on the left or on the right, or on the top or on the right. But as long as I mention who is the root, that's enough. But yeah, on a picture, I will do it more clearly. Definition. A few different types of rooted tree. So special case, or special name of rooted trees. This is just some examples. Shortest path, shortest path. Rooted tree, so it's a name. Is an unoriented graph. There is no orientation. It's an unoriented graph. Oh, no, sorry, unoriented rooted tree. With its root at the unique central vertex. As I mentioned before, for trees, you have only one or two central vertex. So how it looks like, of course, it looks like this. This is a shortest path rooted tree. You can check, compute the distance between any 2 points, and the only one which is at a central place or central vertex is this one. This is called a shortest path, and in applications, these kind of graphs are going to appear again. What is an arborescence? Arborescence. By the way, this is a nice French word. Is an oriented. It's an oriented rooted tree. Can you guess what is arborescence with such a nice word? Can you guess what it is? Everything, all orientations are going outside of the root. Is an oriented rooted tree with all edges pointing out of the root. It's easier to explain it on the picture. You have the root and all edges are going away from the root. The root is on the top. So this is called the arborescence. What is anti? I just use it. I just want to write it. Anti-arborescence. Yes, all pointing are towards the root, which means the anti-arborescence, you would have everybody going to the root. Okay. And I just have a few minutes for the last definition, except if there is any question. Okay, now you can see this kind of unoriented tree is useful. This one, either an arborescence or anti-arborescence, is useful. What is not so useful, I mentioned at the beginning, the definition for trees is not always the best for oriented graph. I mean, this kind of graph, it's still a tree. I'm not sure it's so useful. I haven't seen any application because the orientation are going, I mean, if you think that you can only go in one direction, then you cannot do so much. So that's why the definition for trees was fine for oriented graph as well, but, and so it covers this. This is a tree, an oriented tree. It's probably not the most useful one. Probably either an arborescence or an anti-arborescence is more useful. Still, we have a name for this guy if necessary. Last definition for today. So G, an unoriented rooted tree. And I call root, I'm going to call it R. There's a letter R for root. So any X in the graph, the distance between the root and X is called the height or the depth of X. Okay, these are just few definitions. The height of the depth. What is the height of the tree? You can imagine this is the longest one. So the height of G is the maximum of the distance between the root and any X or any X in G. So the first example here has a height of 3. What are ancestors? So ancestors of X, ancestors of X, and this is also called the ascendant. I guess you can imagine if this is X, the ancestors are going to be these guys. Now you can wonder if X is included or not. Probably not, but you have some depends slightly on the answer in the authors. So what is it? Is this a set of Y in G so that Y is contained in the path between the root and X, in the path between R and X. And we know in a tree, there is only one path. This was one characterization of a tree. So there is only one path between R and X, and all the points inside are called the ancestors of X. And again, depends if you want to include X or not. Then it depends on the authors. Now, what are the children or the descendants? First the parent. 5, those 4. What is the parent of X? You can imagine it's the one just above. How do you write it more precisely? Okay, that's fine. It is the Y inside the set of ancestors with the distance between the root and Y is equal to the distance between the root and X minus 1. There's the one before. I forgot that I can do it now. Now the children of the first the descendants. They are the one going below X. So what are the descendants? X. How do, of course, on the picture, it's quite clear. You want all the points which have X as an ancestor. This is the set of Y inside V, such that X is an ancestor. An ancestor of Y. And what are the children? By the way, maybe you observe I call it only parents without a S, but now I'm going to call children. What are the children or the child? Child of X. This is the set of descendants. The set of descendants Y with the distance between the root on Y is the distance between the root on X plus 1. Okay, I will stop here. Just an observation, and you can think about it. Remark. Only one parent is possible. But any number of children is possible. Why do we have this property?
Because if you have more than one parent, you will have a loop.
Not a loop, a cycle. Yes, this is correct. Think about it. If one point, so there is a root, but suddenly suppose that one guy has two parents, then automatically, indeed, you have a cycle. And in a tree, it's not allowed. So there is only one parent. On the other hand, there is no contradiction to have more than one child. Okay, I stop here. Next week, I will just finish this statement, and then we are going to see applications of trees, because we can do many things with trees. Do you have any question or remark?